Welcome everyone to part 1 of this series of videos about the best methods to convert ketones into alkenes. This presentation is about the Wittig reaction of ketones, that is, the olefination of ketones with phosphorus ylides. In the other 3 videos of this playlist we'll have a look at olefinations with sulfones, silanes, aldehydes, other ketones, various carboxylic acid derivatives, geminal dihaloalkanes, polar organometallics, and finally at olefinations with elemental titanium, the so-called McMurray reaction. On my channel you can also find a similar video playlist about the olefination of aldehydes. If a given target compound appears to be accessible by olefination of a ketone, a direct condensation reaction should be considered first, as those described in part 3 of this playlist. These are the most ecologically and economically sound strategies. Unfortunately, however, the scope of direct condensations is limited, and if the target olefin cannot be prepared this way, some other strategy must be used. Phosphorus ylides generally show the broadest scope, but some alkenes may be more readily accessible with one of the other reagents presented in this playlist. To better understand the background story and context of the Wittig reaction, let's first have a look at the possible outcomes of the reaction of functionalized carbon nucleophiles with ketones. A large number of carbon nucleophiles can add to ketones and yield stable tertiary alkoxides, or, upon protonation, alcohols. This includes ammonium or pyridinium ylides, which usually do not eliminate water or amines and yield stable alcohols after aqueous workup. Diazonium ylides, such as diazoalkanes or diazoketones, can also add to ketones, but the resulting alcohols readily eliminate nitrogen and rearrange to ketones, as shown here. Other aldehydes, ketones or CH-acidic carboxylic acid derivatives can also yield alcohols upon reaction with ketones, but these readily eliminate water. These condensation reactions will be discussed in part 3 of this playlist. If the nucleophilic carbon atom carries a good leaving group, the initially formed alkoxide can displace it intramolecularly and yield an epoxide. This kind of reactivity is typical of sulfonium ylides and of metallated alkyl halides. Then, phosphonium ylides and some metallated sulfones, alkyl halides and silanes can yield alkenes directly upon reaction with ketones. I'll show you the exact mechanisms later. Then there are some electron-rich reagents that form strong bonds to oxygen and can attack aldehydes or ketones nucleophilically at oxygen. Depending on the type of ketone and reagent, a carbanion or a catyl radical will be formed and dimerized to a pinacol. Intermediate titanium pinacolates can fragment and yield alkenes directly, as shown here. If the attacking nucleophile is an electron-rich phosphine, then an alkoxyphosphonium alkoxide can be formed, which will usually undergo intramolecular etherification to yield an epoxide. Few examples of this reaction have been reported, though. The reaction of ketones with phosphines may also yield symmetric olefins directly. An initially formed ketone-phosphine adduct can be deoxygenated by an excess of phosphine, whereby a phosphorus ylide is formed. This ylide can then undergo a normal Wittig reaction with the ketone. Again, few examples of such reactions have been reported and will probably require either a very electrophilic ketone or nucleophilic phosphine and a high reaction temperature. Because epoxides can be converted into olefins by treatment with phosphines, alkenes may also result from ketones and phosphines by intermediate formation of epoxides. It is assumed that the Wittig reaction proceeds by intermediate formation of a phosphoxetane with pentavalent phosphorus. According to recent calculations, this intermediate does not result from a perfectly concerted 2+2 cycloaddition. The CC bond appears to be formed slightly earlier than the PO bond, but this will probably depend a lot on the precise structure of all the starting materials. The triphenylphosphonium group is strongly acidifying. Methyl triphenylphosphonium salts, for instance, are 5 orders of magnitude more acidic than acetone. Phosphonates, on the other hand, are much less acidic than phosphonium salts. Most phosphonium salts are more acidic than ketones, and it should therefore be possible to prepare alkenes by adding a base to a mixture of ketone and phosphonium salt. In order to prevent the formation of enolates and aldol addition products, however, phosphorus ylides are usually generated first by adding a base to a phosphonium salt, followed by addition of the ketone to this preformed ylide. At low temperature in aprotic solvents, phosphorus ylides usually add to ketones faster than enolates are formed by deprotonation, even if the ketone is several orders of magnitude more acidic than the phosphonium salt. When performing Wittig reactions with phosphonium salts of low acidity, such as alkyl or benzyl phosphonium salts, it is important to remove all traces of oxygen from the phosphonium salt and reaction mixture. Strongly basic phosphorus ylides are quickly oxidized by oxygen to carbonyl compounds. I'll show you an example at the end of this presentation. Ylides from highly acidic phosphonium salts, however, such as those prepared from haloacetic esters, are less basic and less nucleophilic and do not usually react with the oxygen. Phosphorus ylides can of course always be generated in dry THF with very strong bases, such as LDA, but for large-scale preparations this is not always a practical or economically sound strategy. As shown here, even enolizable ketones can sometimes be olefinated with phosphonium salts in the presence of weak bases and protic solvents. Here, for instance, the Wittig reaction succeeded with potassium carbonate as base and without stoichiometric generation of an ylide. Such reactions work best with non-enolizable ketones, such as benzophenone, or with ketones that undergo aldol addition only slowly. This is another example of the use of weak bases to generate a phosphorus ylide. Here the olefination was conducted in an aprotic solvent mixture of toluene and cyclohexane, with potassium carbonate and sodium hydroxide as bases. The addition of metallated phosphonates to ketones often yields stable alcohols, unless the nucleophilic carbon carries another electron-withdrawing group. In this instance, the allyl group was enough to promote olefin formation. Strongly acidic phosphonium salts or phosphonates can react with ketones even in the presence of weak bases, such as triethylamine in combination with a Lewis acid, as on this slide. Such conditions, however, are very mild and thus very selective, and may not be suitable for sterically demanding, highly enolized or otherwise unreactive ketones. The conditions here, for instance, could not be used for the olefination of acetophenone. With sodium ethoxide, however, even electron-rich acetophenones can be olefinated with phosphonoacetates. In this example, the ylide was formed before addition of the ketone, but because of the high acidity of phosphonoacetates, addition of the base to a mixture of ketone and phosphonate may also have worked. In DMF as a solvent, even simple alkyl phosphonium salts can be converted into ylides by sodium ethoxide. Here, acetone was olefinated and a good yield of alkene was obtained. Sodium terzbutoxide in toluene can also be used to deprotonate simple alkyl phosphonium salts, as shown here. Alkoxides are, however, not suitable for all types of phosphonium salt. Readily displaceable groups, such as benzyl or allyl groups, may also be cleaved off by alkoxides. I'll show you the mechanism in a minute when discussing side reactions. This is a further example of the use of a tertiary alkoxide as base. Because phosphorus ylides are not very basic, no enolate formation or cyclization of the starting ketoester occurred, and a high yield of olefin was obtained. The ethoxycarbonyl groups also remained unchanged. Sterically crowded ketones will only react slowly with most nucleophiles, including phosphorus ylides. The starting triketone of this example could only be olefinated twice, despite the high reaction temperature and the large excess and repeated addition of ylide. Anyway, it is surprising that the reaction worked at all. Because of its low solubility, deprotonations with sodium hydride can be rather slow. If this base is to be used in the Wittig reaction of an enolizable ketone, it would be advisable to prepare the ylide first and add the ketone afterwards, as in this example. Occasionally, the low solubility of phosphonium salts can also be an issue, and sometimes much higher yields can be obtained by adding small amounts of a chelating solvent, for instance triglyme or ethers of di or triethanolamine. This was the case here, where only low yields of alkene resulted without phase transfer catalyst. Organolithium compounds are strong bases but also strong nucleophiles, and cannot always be used as bases. Simple alkyl phosphonium salts, though, can be cleanly deprotonated by butyllithium, without any phosphine formation by dealkylation. When butyllithium is to be used as base, the ketone should be added after ylide formation is complete, because addition of butyllithium to ketones is exceedingly fast. In this example, an enone was olefinated in good yield with a phosphorus ylide generated with butyllithium. 1,3-dicarbonyl compounds are much more acidic than simple ketones, and therefore more difficult to olefinate with basic nucleophiles. Stabilized phosphorus ylides, however, as the one of this example, can add to 3 ketoesters and form the expected olefins. In this instance, the ylide was brominated before reaction with the ketone, and an isomerized olefin was the main product. Let's now have a look at some further potential side reactions. Ketones with alpha-hydroxy, acyloxy or amino groups may isomerize into regioisomeric ketones. This can cause the formation of unexpected olefins, as in this example. Here, when the Wittig reaction was conducted in acetonitrile, another product resulted than in chloroform. These isomerizations occur by simple enolization and acyl migration, as shown here. Phosphonates devoid of additional electron-withdrawing groups usually yield stable alcohols upon reaction with ketones, as in this example. Formation of a phosphorus-free alkene can sometimes be achieved by heating with aqueous bases. Non-stabilized phosphorus ylides readily react with oxygen, whereby aldehydes or ketones are formed that immediately are olefinated by the remaining ylide. If a solid phosphonium salt is to be used in a Wittig reaction, it should be kept in mind that solids can absorb large amounts of air, especially if the particle size is small. Such solid phosphonium salts should therefore be carefully degassed and kept under inert atmosphere before use. Otherwise, symmetric alkenes may result as byproducts. Phosphonium salts can form phosphorus-oxygen bonds with alkoxides or hydroxide, whereby pentavalent phosphorus derivatives result. These are not very electrophilic, but may undergo phosphorus-carbon bond cleavage by protonolysis to yield highly electrophilic alkoxyphosphonium salts and a hydrocarbon. Here, benzene was formed by protonolysis of the pentavalent intermediate. The butoxyphosphonium salt reacted with butoxide, whereby a phosphine oxide and dibutyl ether were formed in low yield. This means that phosphonium salts with substituents that readily form carbanions may be cleaved by oxygen nucleophiles and should be converted into ylides in the absence of alkoxides or hydroxide. If any of the starting materials contains electron-deficient alkenes, Michael additions are a further potential side reaction. In this example, addition of a deprotonated allylic phosphonium salt to an enone led to a Michael addition, followed by an intramolecular Wittig reaction. Electron-deficient olefins may even be cycloproponated by phosphorus ylides, as in this example. In this case, the keto group was sterically too shielded to compete with the highly electrophilic alkene for the nucleophile. If despite of an excess of phosphorus ylide only a partial conversion of a ketone can be attained, this may be due to deprotonation of the ketone by the ylide. This problem may be minimized by choosing an aprotic apolar solvent and by adding the ketone to the preformed ylide slowly at low temperature. Then, in the presence of strong bases, enolizable ketones may always undergo aldol additions and condensations. With alkoxides, hydroxide or other strong nucleophiles, phosphonates may also be saponified and lose their ability to olefinate ketones. Here are some additional examples of the Wittig reaction of ketones. You can also find this reference list in the description of this video. The next presentation is about olefinations with sulfones and silanes. These are less often used than phosphorus derivatives, but may offer some advantages in special situations. See you then.